Let us start the 7th lecture of the series Bracket Algebra. The essential features of the previous lecture 6 were as follows. We discussed Euclidean space and emphasized that it is a physical or real space. In this space, we deal with ordered collection of real numbers. The space may be one-dimensional denoted by R1 or two-dimensional denoted by R2, three-dimensional represented by R3 or n-dimensional which we denote by Rn, where n is a finite number. In Euclidean space, distance is defined and measured by Pythagoras formula. With the help of scalars or numbers or components, we can present a definition of vectors in this space and connect them by linear operations. Euclidean space is a real linear vector space. In quantum mechanics, state vectors are represented as elements of linear vector space. We also discussed the defining properties of linear vector space with special emphasis or reference to certain operations like addition, multiplication by scalars, commutative operation, and so on and so forth. Example of linear vector space was mentioned, like the Euclidean space R1, R2, R3, Rn, the field of real numbers, the space called real linear vector space, the field of complex numbers, the space called complex linear vector space. Ket is represented by a column matrix and is related to bra as bra dagger and is defined in a linear vector space, say V, also called the Ket space. Dual of Ket is bra. Bra is represented by a row matrix and is related to Ket as Ket dagger and is defined in a linear vector space, say V bar, also called the bra space. If V bar is equal to V, then it is the same space and the space is called self-dual linear vector space. As for example, the Euclidean space. Bra psi ket phi is a number complex in general. Bra psi ket phi is in general not equal to bra phi ket psi. We now proceed to discuss what we mean by a linear independence. Consider a set of Ket vectors, Ket1, Ket2, Ket3 and so on. Suppose we connect them, that is connect the Kets by the relation A1 Ket1 plus A2 Ket2 plus A3 Ket3 plus etc. equal to 0. That is summation over I, Ai Ket I equal to 0, where Ai's are coefficients of Ket I, that is A1 is the coefficient of Ket1, A2 is the coefficient of Ket2, A3 is the coefficient of Ket3 and so on. If this relation holds only for A1 equal to 0, A2 equal to 0, A3 equal to 0 and so on, that is Ai equal to 0 for all I, this means that we cannot connect or interrelate the Ket I's. That is, we fail to establish a connection or link between the Kets, Ket1, Ket2, Ket3, etc. That is, they are independent, they do not fit together. Since summation over I, Ai Ket I equal to 0 with Ai equal to 0 for all I, it means that any Ket cannot be expanded or expressed in terms of the other Kets. So the Kets, that is Ket1, Ket2, Ket3, this series of Kets cannot be associated, and we say that Ket1, Ket2, Ket3, etc. form a linearly independent set. They do not care for each other, do not depend on each other. Let us give an analogy. This is x-axis denoted by I hat, this is y-axis denoted by j hat, and this is z-axis denoted by k hat. Now I hat dot j hat is equal to 0. This implies that I hat has no component along j hat. In other words, I cap does not depend on j cap. Similarly, the relation j cap dot k cap equal to 0, implying that j cap does not depend on k cap, and k cap dot I cap equal to 0 means that k hat is not bothered at all about I cap, that is, does not depend upon I cap. Clearly, I cap, j cap and k cap have no components along one another and cannot be associated in any way. Still, if we forcefully write a relation A1 I cap plus A2 j cap plus A3 k cap equal to 0, then obviously it holds only for a1 equal to 0, a2 equal to 0, a3 equal to 0. We thus conclude that I cap, j cap and k cap are linearly independent. The analogy being over, let us now focus on to what is meant by linear dependence. Consider two kets, ket1 and ket2. They are connected by the relation a1 ket1 plus a2 ket2 equal to 0, where a1, a2 are coefficients, and let us suppose that a1 is not equal to 0, a2 is not equal to 0. This means that we have found an interrelation between the kets. Clearly, as they are linked or associated through a relation, we can express one ket, say ket2, as some constant alpha into ket1. So one ket can be expressed in terms of the other ket. It also follows that ket2 and ket1 are in the same direction, since ket2 is equal to some constant into ket1. We conclude that ket1 and ket2 are linearly dependent. Why linearly? Since they, that is the kets, ket1 and ket2, are both raised to unit power in the relation a1 ket1 plus a2 ket2 equal to 0. We now consider three kets, ket1, ket2 and ket3, related as a1 ket1 plus a2 ket2 plus a3 ket3 equal to 0, where a1 is not equal to 0, a2 is not equal to 0, a3 is not equal to 0. This means that we have found an interrelation between the three kets, ket1, ket2, ket3. And since the three kets are associated or connected, we can surely express or represent one ket, say ket3, in terms of the others, as ket3 equal to some constant alpha into ket1 plus some constant beta into ket2. In other words, ket3 can be expressed in terms of the other kets, that is in terms of ket1 and ket2, that is ket3 linearly depends on ket1 and ket2, as all the kets are raised to unit power and the relation is a linear relation or connection between the kets. If we suppose that a3 equal to 0, then the relation reduces to a1 ket1 plus a2 ket2 equal to 0. This means that ket1 and ket2 are linearly dependent, while ket3 is linearly independent since we fail to link or connect, that is associate ket3 to the other kets in this case. And if a2 equal to 0, then the relation gets further reduced to a1 ket1 equal to 0, and this then gives a1 equal to 0. So all the coefficients a1, a2, a3 are 0. So then all the kets ket1, ket2, ket3 becomes linearly independent, that is unconnected in this case. If a1 ket1 plus a2 ket2 plus a3 ket3 plus etc. is equal to 0, that is summation over I, ai ket I equal to 0, where ai's are not equal to 0, that is a1 not equal to 0, a2 not equal to 0 and so on so forth, then ket1, ket2, ket3 etc. form a linearly dependent set or combination. Let us cite an analogy. This is I hat and this is j hat, and here is vector r. It is a 2D space. Consider the relation vector r equal to rx I cap plus ry j cap, and vector r equal to r into r cap. This implies, now let us put r to be a1, minus rx to be a2 and minus ry to be a3, and rewrite the relation as clearly r cap, I cap and j cap are linearly dependent, as vector r can be expressed in terms of I cap and j cap. But let us note that I cap, j cap form a linearly independent set, since if we by brute force try to connect them as, then it holds only if the coefficients vanish, that is, we cannot really connect I hat and j hat in any way. We next turn our attention to what we mean by the words span, expansion postulate, and principle of linear superposition. Consider a linear vector space having n independent directions. Let the kets along these n directions be ket1, ket2, ket3, etc. Then any other ket, say ket psi, in this linear vector space can be expressed as a linear combination of ket1, ket2, ket3, etc. as ket psi equal to c1 ket1 plus c2 ket2 plus c3 ket3 and so on. that is ket psi equal to summation over I Ci ket I. C1, C2, C3, etc. are called expansion coefficients. We say that ket1, ket2, ket3, etc. span the linear vector space. In other words, these kets are able to encompass, that is, completely cover the entire linear vector space by themselves. This is just like considering an arbitrary vector R in 2D that can completely be described by the unit vectors I cap and j cap, which thus span the entire 2D space. We shift our focus now to basis of linear vector space. In a linear vector space, consider a set of kets, ket1, ket2, ket3, etc. along all independent directions such that a1 ket1 plus a2 ket2 plus a3 ket3 plus etc. equal to 0. That is summation over I ai ket I equal to 0, and this holds for ai equal to 0 for all I. That is ket1, ket2, ket3 etc. are linearly independent. Let ket psi be an arbitrary ket in the linear vector space expandable as C1 ket1 plus C2 ket2, C3 ket3 and so on. That is ket psi equal to summation over I Ci ket I, where Ci is the expansion coefficient for ket I. That is C1, C2, C3 etc. are the expansion coefficients of the kets ket1, ket2, ket3 etc. respectively. So ket1, ket2, ket3 etc. span the linear vector space. Under satisfaction of these two criteria, namely linear independence and principle of linear superposition, the set of kets ket1, ket2, ket3 etc. are said to form a basis in the linear vector space. We make a gist. To form a basis in linear vector space, ket1, ket2, ket3 etc., that is ket I, should be linearly independent, satisfying, and should span, that is, any arbitrary ket psi in the linear vector space should be expandable as a linear combination of these ket i's. If in addition to the above two criteria, the basis ket I, that is ket1, ket2, ket3 etc. are orthonormalized, then the basis ket I is called orthonormal basis. An orthonormal means orthogonality plus normalization. Let us put things in a nutshell. Basis of linear vector space should be linearly independent and should span. These are the essential features and may be orthonormalized, which is a desirable feature. Next, we prove certain very important statements. The first one is that basis is not unique. There can be multiple sets of bases of a linear vector space. Consider R2 space, that is a 2D region defined by the unit vectors e1 cap and e2 cap, and vector alpha is an arbitrary vector in this space. To describe R2 space, let us make the first choice of basis as e1 cap and e2 cap. We note that a1 e1 cap plus a2 e2 cap equal to 0 holds if a1 equal to 0, a2 equal to 0. This means that e1 cap and e2 cap are linearly independent. Again, vector alpha can be expressed as c1 e1 cap plus c2 e2 cap. So e1 cap, e2 cap span the R2 space. Again, ei cap dot ej cap equal to Kronecker delta ij, which means that e1 cap, e2 cap are orthonormalized. Let us try a second choice of basis. Construct vector f1 equal to e1 cap plus e2 cap whole divided by under root 2, and vector f2 equal to e1 cap minus e2 cap whole divided by under root 2. Relate vector f1 and vector f2 through the relation a1 vector f1 plus a2 vector f2 equal to 0. This implies that a1 equal to 0, a2 equal to 0. So a1 into vector f1 plus a2 into vector f2 equal to 0 holds only if a1 equal to 0, a2 equal to 0. This implies that vector f1 and vector f2 are linearly independent. The first criteria for vector f1, vector f2 to be basis vectors is satisfied. We express the arbitrary vector alpha in terms of vector f1 and vector f2 as vector alpha equal to c1 vector f1 plus c2 vector f2. Putting expressions for the vectors f1 and f2, we have vector alpha equal to c1 prime e1 cap plus c2 prime e2 cap, which is expansion of vector alpha in terms of e1 cap and e2 cap, that is justified since e1 cap and e2 cap are basis vectors. So the expansion of vector alpha in terms of vectors f1 and f2 that we started with is justified too. So vector f1 and vector f2 span the 2D space. We check orthonormalization. Vector f1 dot vector f1 is 1 and vector f2 dot vector f2 is also 1. So vectors f1 and f2 are normalized. Also vector f1 dot vector f2 equal to 0, and so vectors f1 and f2 are orthonormalized. We thus conclude that the 2D space can be described by two bases e1 cap, e2 cap, as well as by vectors f1 and f2. Next statement that we make is that linear independence does not imply span. Consider the unit vectors e1 cap and e2 cap along x and y axis respectively. They are linearly independent, but they do not span R3, the 3D space. This means that e1 cap, e2 cap is not a basis of R3, the 3D space. Next statement that we make is that span does not imply linear independence. Consider vector A in R3, the 3D space. Suppose vector A is expressed in terms of e1 cap, e2 cap, e3 cap as, which can be manipulated, and finally we end up with vector A being expressed as a linear combination of four vectors e1 cap, e2 cap, e3 cap and e4 cap. This suggests that the four vectors e1 cap, e2 cap, e3 cap, e4 cap spans the 3D space. But note that e4 cap is actually a linear combination of e1 cap, e2 cap, that is, it depends on them. So the set e1 cap, e2 cap, e3 cap, e4 cap is not a linearly independent set, so they cannot represent a basis R3. Question: can you treat the set as basis of R3? The answer: let vector f1 be e1 cap, so defined. Vector f2 equal to e1 cap plus e2 cap whole divided by under root 2, and vector f3 equal to e1 cap plus e2 cap plus e3 cap whole divided by under root 3. Check linear independence. Consider the relation a1 vector f1 plus a2 vector f2 plus a3 vector f3 equal to 0. Putting values of vector f1, vector f2, vector f3, we get as e1 cap, e2 cap, e3 cap are linearly independent, coefficients are 0. This leads to a1 equal to 0, a2 equal to 0, a3 equal to 0. This means that vector f1, vector f2, vector f3 are linearly independent. Next, check span. Consider an arbitrary vector A expressible in terms of vectors f1, vector f2 and vector f3. Replacing them with their values, we end up with this is expansion of vector A in terms of e1 cap, e2 cap, e3 cap. So vector A is expressible as a linear combination of the vectors f1, f2, f3. This means that vector f1, vector f2, vector f3 span R3. So we conclude that the vectors f1, f2, f3 form a basis of R3. Let us check if they are orthonormalized. We find that vector f1 dot vector f2 is not 0. So the vectors f1, f2 and f3 are not mutually orthogonal, and hence the set is not orthonormalized. Check normalization. Vector f1 dot vector f1 is 1. Vector f2 dot vector f2 is 1. Vector f3 dot vector f3 is also 1. So vector f1, vector f2 and vector f3 are normalized to unity, and so we can rewrite them also as f1 cap, f2 cap, f3 cap respectively. Let us end this discussion posing a question: what is Hilbert space, that we take as the topic of lecture 8.